All right. In this lecture, we're going to talk in more detail about gas phase mechanisms. So we've previously discussed in this class and probably in your other classes that reactions with gas phase molecules can be initiated when the molecules collide with each other. In this lecture, we'll look deeper into what that means. So one thing that can happen when two gas phase species collide with each other is that they can react. So for example, if we have a highly reactive species, such as maybe a radical, and this is in the gas phase, and this is going to collide with another such species, these two things can absolutely react. They don't necessarily have to react, but they can. This is kind of a special case, though, because those two intermediates are really highly reactive because they're radicals. So basically, if they collide with each other, they are very highly active. They're going to want to form that bond. Now, there's reasons they might not form the bond. Maybe they hit at an angle that doesn't allow the two open sites on the molecules to form that bond, so they don't necessarily have to. They could, collide and bounce off each other, but probably they're going to react. However, more often when these gas phase molecules collide with each other, and recall that they're traveling very fast, so they're moving very quickly. They got a lot of momentum, at least on the scale of a molecule. So even if they don't form a reaction, when they collide, something's going to happen. And often what happens is that they form what we call active intermediates. And so a way that we can denote that for a general species, let's call it A, and that's going to collide with something else, we'll call it M. M we're just using as kind of a vague term. M could be another species, it could be a molecule, it could be a dust particle, something. So A collides with M and forms an activated intermediate, which we're going to denote with a star. So this is confusing because we're also using star or asterisk to denote a catalyst site. It's a completely different meaning. It's not meant to be, we're not using the same notation here to try and convey that those two things are similar in some way, because they're not. This is just one of those annoying things about engineering notation where we use the same symbols for things that could be construed as being similar but really aren't, and so we create confusion. Long story short, basically this is just a way that we're denoting this, and it is not related to the fact that we also denote catalyst sites with the asterisk. All right, so A star is an active intermediate. So an active intermediate is going to be a high energy molecule that reacts, I didn't write that very clearly, reacts virtually as fast as it's formed. So it's an activated molecular complex. So during the collision, kinetic energy from the collision is transferred into internal energy in the molecule. Internal energy in a molecular complex or a molecule or a chemical species, that's going to comprise electronic, vibrational, and rotational contributions. So these electronic, vibrational, and rotational contributions, these arise due to the molecular and electronic structure of this gas phase molecule or species. So essentially, how are the nuclei arranged? What are the charges on those nuclei? And hence, how do the electrons arrange around them? That's what define essentially all of these contributions. The electronic contribution is the potential energy that's stored within the bonds of the molecule. the vibrational energy is another type of energy, is how the different nuclei move with respect to each other. It's a quantum chemical phenomena. And then the rotational contributions also have to do with the molecule and how it rotates around, which also have to do with its shape. So all of these are based on essentially the nuclear arrangement and the resulting electronic structure. That is a long way of saying that essentially the energy is absorbed into the chemical bonds of the molecule. So just to refresh, because I went off on a little bit of a tangent there, we have a collision between two chemical species. They're traveling really fast, very fast. There's a lot of energy in that collision. That's transferred into the chemical bonds of the molecule. This causes perturbation of the electronic structure. So now you kind of see what's happening here if you transfer a lot of energy into the chemical bonds, and that energy is basically going to, you transfer a lot of energy into those chemical bonds, what's basically going to happen is it could become an excited state. So you're giving it enough energy that the molecule adopts a excited electronic state. It could result in a molecular rearrangement. So maybe it forms a different conformation because due to this energy transfer. It could also result in breaking or forming of new bonds. All of these things, with maybe the exception of breaking and forming new bonds, basically you're looking at a perturbed molecule and an excited molecule. They're going to have a short lifetime, and hence, because of that, we can model them using the pseudo steady state hypothesis. So let's do that for an example. So this example is going to be the azomethane decomposition reaction. It's proposed to occur by the following mechanism. So this here is going to be azomethane. In one step, two azone methane molecules collide with each other. In doing that, energy is transferred to one of them. So maybe based on the energy of the collision and also the orientation of the collision, one of those molecules comes off being an activated complex. That's what we're showing there. The activated complex can collide with some other molecule, say another azomethane molecule. If it collides with an azomethane molecule, then what happens is that it becomes unactivated. So this collision that transforms it into an activated complex, now I have an activated complex. If that collides again without anything happening, what happens there is that it becomes, it goes back to its original state. So that's one possibility. So the activated species collides with something and becomes unactivated. So it goes back to just azomethane. Another thing that can happen is that this species, before it collides with something else, it can decompose into ethane and nitrogen. So you can imagine what happens here. You have these two azomethanes, they collide, one of them becomes an activated species complex. What's probably happening there is that the bond between the ethane complex and the nitrogen complex becomes excited or elongates and tries to vibrate faster than it was before. Two possibilities happen. One, it collides again and it's like, okay, goes back. The other possibility is that, okay, those two things split and you have two species, your ethane and your nitrogen. Okay, so let's make some assumptions here. Or let's make some modeling decisions here. We're going to say we have essentially two reactions. This is going to be one reversible reaction. So essentially reaction 2 is the reverse of reaction 1. So that will say reaction the collision is a reversible process, and we'll say that the second or the third reaction, which is really our second reaction, we're going to say that's irreversible. So essentially what's happening in reaction 1, we have two azo molecules collide. Oops, that's not the right way to spell that. Collide, forming one active intermediate. Say one of the azo molecules it acts more like a catalyst than a reactant or product here. So maybe I should say the other. And a reactant or product. And I will fix my spelling here. The asterisk species means that the species is an active intermediate. It's likely an excited state or a conformational change. Since there is no stoichiometry change. And when I say excited state, that could be an electronically excited state, it could be a vibrationally excited state. So you have some normal vibrational mode that vibrates faster, for example, or more vigorously, which would allow that dissociation to occur. Reaction 2, this is the reverse of reaction 1. That is why we're going to call it reactions 1 and 2 as one reversible reaction. In reaction 3, we have the active intermediate decomposes into ethane and nitrogen. So what are the intermediate species in this mechanism? That's going to be our activated complex. In the pseudo-steady state hypothesis, our intermediate species have short lifetimes. So this species is going to have a short lifetime. It's basically formed through a collision, and what it does is either goes back to its unactivated state, or it decomposes. So it doesn't have a very long lifetime. All right, so let's then write the rate law for formation of ethane and use the pseudo-steady state hypothesis then to come up with a rate law. So to get the rate law of ethane, we're going to use, ethane is only involved in reaction 3, so we're going to use this reaction. We're going to say RC2H6 is equal to K3 times C azo. And then we can get C azo using the pseudo-steady state hypothesis. So what we want to do now is write a net rate of formation of azo. We're going to set that equal to 0. And I'm sorry, I should say when I'm doing that, I mean the activated part of this. So I want to write, I need that concentration, and I'm going to get it using this pseudo-steady state hypothesis. And I need that concentration because it's involved in my net rate of ethane formation. All right, so this activated complex involved in reaction 1, 2, and 3. So I'm going to write the rates for each of those. I'm going to say it's equal to K1 CaZO squared. So that's the forward rate of reaction 1. So that is how this activated complex is formed. It is consumed through the reverse process. So that's going to be the concentration of the activated complex times the concentration of, what do we call this, azomethane? Yes. And then it again is going to be further consumed if it reacts to form ethane and nitrogen through reaction 3. So now I can start solving for this. I actually have to go to a meeting, so I'm going to take a break and do that subsequently. All right, I'm back. Okay, so we've developed this expression for the net rate of the formation of this activated complex based on the mechanism. And now what we want to do is use this to solve for the concentration of the activated complex. So we're going to do that. So this is going to be an algebraic manipulation. Basically what I'm going to do here is separate out this quantity, or this variable. And solve. I can simply rearrange this expression that gives me my concentration term. Now I can substitute this concentration term into my rate expression for ethane. Notice in doing this that everything, or at least all the concentration terms in this rate expression, I can measure. So I can measure the concentration of azomethane. I cannot measure the concentration of the activated complex of azomethane, and that's because it just doesn't have that a long enough lifetime to be able to do that. So the purpose in solving for it is to be able to eliminate it from this rate expression. And the model I've chosen to do that is the pseudo-steady state hypothesis. So we've also talked in class, or maybe we will talk in class, about using the rate determining step method. That's another method for essentially writing a rate expression, and part of the solution procedure there is to relate the concentrations of the intermediate species, or maybe the surface coverages of the intermediate species, back to a gas phase concentration. That's again because it's easier to measure the concentration of the gas phase species than it is the surface phase species. So both of these methods, that's essentially what we're doing. We're picking a model to be able to get an expression for a concentration that we cannot measure or is not straightforward to measure, and base that on the concentration of a species that is easy to measure or is straightforward to measure. So that's what we've done here. Now we have a rate expression for the formation of methane. And our question asks us, what are the apparent reaction orders at high and low concentration of azomethane? So let's look at that under two limiting scenarios. So say limiting scenarios. So theoretically, if the mechanism that we've written is always valid, then this is the rate expression always, and this should be global. Let me say that may or may not be true. Anyways, I'll just leave it at that. But under certain limiting scenarios, our rate expression is going to start to approximate slightly different expressions. So let's look at high concentration of azomethane. if we have high concentration of azomethane, what that means is that this term in the denominator, this first term, is going to be significantly larger than the second term in the denominator. In that case, the rate of ethane formation is going to be approximately equal to some rate constant, let's just call it K prime, times the concentration of azomethane. So what's happening there is that if we go back to our rate expression, if this term is much greater than this term, then essentially the rate expression is going to be equal to K3 K1 C azo squared over K2 C azo, which is going to be approximately equal to some effective rate constant that engulfs all three of these times C azo. So if we were doing an experiment at high C azo or a high concentration of azomethane, that is what we would probably observe, right? So an experiment is going to give us a kind of a singular observation. It can't give us the amount of detail that we need to get all of these pieces. So this is what we would observe in those circumstances. So let me get rid of all of this. Okay. So high concentration of azomethane, we're going to get something that looks like a first order reaction. At low C-azo, I basically have the opposite thing going on. In that case, I have K3 is going to be much greater than K2 times C-azo. In that case, if I go back to my rate expression, then what that's going to look like I'm going to look something like this. So that's going to, at low concentration of azomethane, this first term actually drops out because maybe it's so low that it's near that term is near zero. In that case, my rate expression looks like K1 C azo squared. So I'm going to have a second order. If I was going to do an experiment here, it would look like it was second order in azomethane. A nice thing here is that then it's possible to approximate what that K1 value is equal to. So I would have here RC2H6 is going to be approximately equal to K1 times C azo squared. So I have here a parent first order, and here I have a parent second order. And you can also see here how running this, if you're going to run an experiment to try and learn the rate law for this reaction, say you did not know the mechanism, but you had kind of hypothesized what it might be. You might say, okay, I'm going to run this experiment at high and low concentration of azomethane, see if I get different results and different reaction orders, and that's going to help me provide credence or maybe disprove the hypothesis I made about the mechanism.